So lesson 2 in this complex numbers pack is concerned with the modulus argument form of a complex number. So far you know how to write complex numbers in what we call Cartesian form, so x plus iy or a plus bi or whatever. But there are different ways of representing complex numbers, one of which you'll meet here, which is modulus argument form. This is a really important form of complex numbers for you to know about. Which basically represents them as a distance from the origin, which is the modulus, and an angle measured from the positive real axis, which is the argument. You can have a look at this diagram here. So given a complex number on the argand diagram Z plotted here, this has got essentially coordinates x and y. If you wanted to work out the distance from the origin r, we can use Pythagoras for this. So it's just x squared plus y squared. And if you wanted to work out the argument theta, we're going to use trig, so we can use tan. From this diagram here, you can see that if we take this as a right angle triangle, which it is, so x is the adjacent side, r is the hypotenuse, so we can say that cos theta equals x over r, which leads you into this relationship between x and r and theta. X is r cos theta. Likewise, for the opposite side, that's our y coordinate. So we've got the opposite is y. R is the hypotenuse, so we can use sine to say sine theta is y over r. And then you can rearrange this for your relationship between y and r and theta. So you can swap this into Cartesian form and say that z equals r cos theta plus ir sine theta, or we usually factorize out the r. And this is what we call modulus argument form of a complex number, r, and then brackets cos theta plus I sine theta. So expressing complex numbers in modulus argument form is a useful thing to do. So for this complex number here, first thing I'm going to do is calculate the modulus, which remember is just Pythagoras. I'm not concerned with the minus, and I don't include the I when I calculate this. So I get 4 root 2 for the modulus of this complex number. For the argument, it's worth doing a little sketch on the argand diagram and see where this is. So minus 4 to the left, 4 up, so it's up here. And our argument is measured anti-clockwise from the positive real axis, so it's that obtuse angle in there. I'm going to work out the acute angle and take that away from pi. This is a right angle triangle here with side lengths 4 and 4. So inverse tan 4 over 4, that's pi over 4. So we're going to get our argument of 3 pi over 4 for this one. We can represent z then in modulus argument form as the modulus on the outside of the bracket, 4 root 2. And then on the inside, we've got cos 3 pi over 4 plus sine 3 pi over 4. Things to note about this is that the angle must be the same in both the cos and the sine, and it must be a plus in between them. If there's a minus, it's not modulus argument form. But there are things we can do. We'll come across that later. Example 2. So we've got the modulus and argument of a complex number this time. Now it wants us to express it in modulus argument and Cartesian form. So easily enough, we can write modulus argument form as 8 on the outside of the brackets, cos minus pi over 3 plus I sine minus pi over 3. Working this out in Cartesian form, we're just going to go into our calculator and we're going to work out each individual bit of this. So my first bit, I've got 8 cos minus pi over 3, which gives me 4. And then for my sine bit, I've got 8 sine over 3. Which is minus 4 root 3. So minus 4 root 3i. There are 2 u tries there. I recommend you pause the video and have a go at those, and then I'll reveal the answers. So for this first one, you should have got the modulus is root 13 and the argument is 2.55. So modulus argument form, we've got root 13 cos 2.55 plus I sine 2.55. For this one here, you get in modulus argument form, you just write it in there. So 2 cos 5 pi over 6 plus I sine 5 pi over 6. Typing those bits into your calculator, you get minus root 3 plus I as your Cartesian form. There's a bit here about how your calculator can convert between Cartesian and modulus argument forms. Typically, I don't use this, but feel free to have a go at this yourself if you like. Now, modulus argument form is particularly useful for doing multiplication and division of complex numbers. You do already know how to do this by, like expanding brackets out or rationalizing the denominator in a fraction, but in modulus argument form, this becomes super easy. There's a proof of it here using the addition formula for trig from Signal Maths. You don't need to learn this proof, it's just for your own interest here, really. The important part about this are the results in the boxes down here. So it turns out if you multiply two complex numbers together in modulus argument form, you are allowed to multiply their moduli together. And to work out the new argument, instead of multiplying the arguments, you add these arguments together. Similarly, for dividing complex numbers in modulus argument form, you divide their moduli and you subtract their arguments from each other, and this gives you a quick way of doing these calculations. Finally, for conjugation, I mentioned earlier, something isn't in modulus argument form if there's a minus in between the cosine and the sine. So usually for complex conjugation, if it was x plus iy, your conjugate would be x minus iy, as you can see on here. But the conjugate of a number in modulus argument form isn't just r cos theta minus I sine theta. This is not in modulus argument form because it's got that minus in the middle. Instead, what we do is this. So look at this diagram here. So z has modulus r and argument theta. Z conjugate is a reflection in the real axis. So Z conjugate is down here. It's got the same modulus, the same R. It's got the same angle with the real axis, but it's below instead of above. So it's the same angle, but negative. Okay. So instead of putting the minus in the middle, you put the minus in front of the argument for Z conjugate in modulus argument form. There are 3 examples here. I'm going to work through all of these, then pause the video. And then you can pause the video so you can have a go at them yourself, and then I'll reveal the answers. So first off, this multiplication here, rather than expanding all this out, which I really don't want to do, or convert it into Cartesian form I don't want to do, I can use the results that we previously talked about. So multiplying complex numbers together means I'm allowed to multiply their moduli together, which is 2 and 1 over 3. And then for the arguments, I add their arguments together. So I've got 3 pi over 4 plus 2 pi over 3 plus I sine 3 pi over 4 plus 2 pi over 3. And then we can simplify this in here. 2 cos 17 pi over 12 plus I sine 70 pi over 12. Be mindful of these arguments. Usually they're required to go in a certain range, usually minus pi to pi, sometimes 0 to 2 pi is fine. If you did need to change them, you just add or subtract multiples of 2 pi. This one we'll say is fine because it's bigger than pi, so 12 pi over 12 will be pi, but it's less than 2 pi, which will be 24 over 12 pi. So we'll leave this one as is, it's fine. For this second example, now we're dividing these complex numbers, so I'm going to divide their moduli. So 2 divided by a third, which gives me 6. And then for their arguments, I'm going to subtract those. So 3 pi over 4 minus 2 pi over 3 plus I sine, same thing, 3 pi over 4 minus 2 over 3. So this will give us 6 on the outside, and then cos of pi over 12 plus I sine pi over 12. On the final example here, one thing to note is that the bottom number is not in modulus argument form. It's a complex conjugate because it's got a minus in the middle, but it's not in modulus argument form. So to deal with that first, leave the top as it is. I'm going to change this to the cos of minus 2 theta plus I sine of minus 2 theta. Remember, this is how we conjugate in modulus argument form. Now I can go about dividing the moduli, so I get 2 over root 3, and I subtract the arguments, cos 3 theta minus minus 2 theta plus I sine of the same thing. We can rationalize the denominator, 2 root 3 over 3, and 3 theta minus minus 2 theta gives me 5 theta. Pause the video now and have a go at those three, and I'll reveal the answer. So for the first one, here's what you should have got. So 3 over 2 on the outside, minus 11 over 12 pi on the inside. For the second one, we're dividing their moduli to getting 6 and subtracting their arguments, getting 5 pi over 12. And finally, for the last one, deal with the minus on the top. So that should change to minus 3 theta inside the brackets. Divide those moduli, so you get 3 over root 3, which just simplifies to root 3, and subtract that argument gives you minus 5 theta. One more over the page here, which requires a little bit more work. So we're being asked to find I, Z over W conjugate here. To be able to apply the modulus argument multiplication and division rules, I need to write I in modulus argument form. In modulus argument form, I has a modulus of 1, and its argument is pi over 2. If you think about it on an Argand diagram, I is up here, so it makes an angle of 90 degrees with the positive real axis. Okay, so I can write this as 1 cos pi over 2 plus I sine pi over 2. Now we can put all this together. So I is 1. You don't need to include the 1, but I'm going to. I sine pi over 2. Z from the question is 4 cos pi over 4 plus I sine pi over 4. And that's over W conjugate. Remember, we changed the sign on the argument for the conjugate, so that'll be 3 cos positive pi over 3 plus I sine positive pi over 3. We needed to say plus in between those. I'm going to deal with these a pair at a time. So deal with the top of this fraction first. So we're going to multiply the moduli together to get 4. And we're going to add their arguments together to give me 3 pi over 4 plus I sine 3 pi over 4. That's still over 3 cos pi over 3 plus I sine over 3. And then we're going to divide their moduli to get 4/3, and we're going to subtract their arguments from each other. So I'm going to do 3 pi over 4 minus pi over 3, which is going to give me 5 pi over 12 plus I sine 5 pi over 12. Pause the video, and then I'll reveal the final U-try. So similar thing for this one, you should have ended up with 6 cos pi over 12 plus I sine pi over 12.